thank you, Enrique, for this kind introduction. Yeah, that's precisely the summary of what I'm going to talk about. I would like to talk about challenging optimal control problems from practice, from academia, and how one can solve them even when they are very large. And I would like to spend the first half of my talk on model predictive control and the second half of my talk on reinforcement learning. This is material that has been, well, has evolved over the last 10, 15 years, so there are a lot of co-workers. I would particularly like to point out two co-workers for this use case, which is a real industrial use case, which is by Matthias Höger, who's a former student of mine, and Kilian Link, who are both at Siemens Energy here in Erlangen, just, I think, 500 meters away. Yeah, so let me start with a brief introduction. What is this all about? This is about optimal control. So we need some control system, and let me start right with a formula. So this is a control system here in continuous time where we have a differential equation. This is a control system in discrete time where G defines the next state at a discrete time instant. And for this talk, it doesn't really matter. It will apply to both more or less. I will, of course, not do everything for both models, but I will switch from one to the other occasionally, whatever is more convenient. Okay, so X is the state. This is what we want to control. U is the control input. That's the variable time depending that we are allowed to change according to our needs. And many control problems, particularly if they last longer than just a few seconds or whatever the dynamic scale is, will require optimal control in feedback form. What's a feedback control? A feedback control means that we do not pre-specify this control u of t as a variable or as a function of t for a long time into the future, but actually we would like to have our control as a map f that takes the state or a measurement of the state and produces the control value from that. And the name feedback is completely clear. We look at what the system is doing, and this feedback from the system tells us how to control it in the near future. Yeah, the reason for that is that with the feedback, we are much more able to correct deviations, and deviations are everywhere. We have modeling errors, we have perturbations that we have not foreseen. And just to show you a little quick example, it's this one. This is a pendulum example that a student of mine did a while ago. So it's a swing up of the pendulum. This, of course, you could do with open loop. But then the feedback is needed because the student is going to tease the pendulum, and the sensor realizes that the pendulum is pushed and reacts to that by, well, swinging it up again if necessary and making corrections. That's the mechanism of feedback. That is what provides the robustness that we want to have in most practical applications. Okay. Now, I would like to talk about control problems on infinite horizon today. There are many interesting control problems that are on finite horizons, but I would like to go to infinite horizon as a model problem. And of course, nothing in the world is really infinite, but infinite horizon models are the models to, are the models for control processes that last for an indefinite and undetermined amount of time. So if there's no natural ending to the process, then this would be the right model. What we want to minimize is we have a so-called cost function, which is this L. We plug in the state, we plug in the control, we integrate everything over t in continuous time, or we sum over t in discrete time, and then we get a quantity, which of course a priori might also be infinite or minus infinite, but this quantity we would like to minimize, right? So it's always minimization today. And a very classical example, that's what we used in the pendulum, is that you have a desired state, this x hat, which in the pendulum was the upright pendulum and the car in the center of this little track where it went. And then you penalize just the distance of the current state from this desired state, and you also can penalize the control effort with the weight lambda, and this would be what is called tracking control. But that's a very special form, and very often you would look for something which is much more, well, economically inspired, where you want to really minimize some energy cost or want to maximize a yield. We will see this in the use case in a few minutes. Okay. Now, an object that is very helpful, and this is a theory that comes from the 1950s, is the so-called optimal value function. So what do? We fix the state x, which is the initial state where our motion starts, and we optimize over all possible controls U, so that what we get is the best possible value that is reachable from this, or that is achievable, I should say, from this initial state, right? And this optimal value function has a very rich structure, and in particular it is known, this comes from work of Richard Bellman in the 1950s, that it satisfies an equation. In continuous time, it satisfies this so-called Hamilton-Jacobi-Bellman equation. That's a first-order partial differential equation. In discrete time, it satisfies this so-called Bellman equation, which is still a functional equation because the unknown v is a function, but it's not a differential equation. It's more like an algebraic equation on this. Why is this important? You should say I'm maybe interested in the feedback law, not in the optimal value function, but there is a very close relation, namely that you can get the feedback law, the optimal feedback law, as the minimizer of these equations. So you take this left-hand side here of the equation, and then you just look at what is the u that minimizes this expression here or there, and this would be the optimal feedback law. Well, actually it's the other way around. If we find an optimal feedback law, it satisfies these conditions. If we have these conditions satisfied, there may still be technical problems like regularization problems that may prevent us, particularly in this partial differential case here. But nevertheless, conceptually, the optimal value function tells us something about the optimal control. Okay, now, as I said, there are regularity issues which I will not talk about. This is really something which can be very difficult, so it may not work as easily as it sounds, but even if it is possible, in discrete time it's much easier, right? There is not so much technical difficulty. There is a main conceptual challenge, it's the so-called curse of dimensionality. And the curse of dimensionality means that if we solve these equations, think of a PDE, you would think of finite element methods, finite volume methods, whatever, something like that. If you try to solve that with traditional techniques, you will need an exponential amount of unknowns to represent your functions, right? So the numerical effort usually grows exponentially with the space dimension. That's quite easy to see. So assume, for example, that you, in your discretization of the state space, 10 points in each direction is enough, which is actually little, but let's just assume for the sake of the argument. Then, of course, for d equal 2, for 2 dimensions, you need 10 in this direction. You need also 10 in this direction. And then, of course, you need to fill the whole square. So this means that you need 10 by 10 is 100. If you add another dimension, you will need another 10. But then you will also have to fill the whole cube then, which will be 1,000. So that means that if you let the dimension grow, the number of discretization point grows exponentially, and that's usually related to the number of unknowns that you need to compute if you want to do this numerically. So, and the problem then becomes really quickly computationally infeasible. I'm just reading a PhD thesis of a candidate who did this approach with a classical gridding technique for an aerospace problem, really as an industrial problem. It's a d 6, and it's really, so you need to pull all the tricks in your code to get that running for d equal to 6. It's really d equal 9, 10, 20, 100 is completely out. Okay, and this is also not an overly pessimistic result in general. If you just think of, you have some arbitrary complicated functions, and these optimal value functions can be quite complicated, you will really need this number of points, right? For general functions, there's no way around. So what we need is some kind of redundancy, some kind of complexity reduction that we can exploit, right? I would like to talk about some things that, of course, most of you will know that they have been done a lot in order to reduce complexity. Model order reduction is probably the first thing you would think of if you want to reduce the number of states. So you replace your big model with, I don't know, 500 states by a small model with 20 states, which does essentially the same, right? That's the idea with model order reduction. Then there is this recent stream of research on the Koopman operator. In this case, you would not necessarily reduce the number of states, but you would probably be able to trade in some nonlinearity and get something which is linear, maybe a bit higher dimensional, but linear is always nice and also gives you some redundancy. There are some more exotic things like the using the compositionality of vector fields and flows. But the common feature of all these methods I'm mentioning here is that they take the model, right? They look at the model, at your differential equation or your discrete time model, and try to simplify that to get something which still describes reality with a certain accuracy, which is good enough, right? And what I would like to propose here is actually a technique that looks at the solutions. So maybe your model is complicated, is high-dimensional, has nonlinearities, but still the optimal solution, because you want to optimize, maybe this optimal solution can be realized with a rather simple structure that has some redundancy. And that's the idea here. So the complementary approach that I would like to talk about today is to use the redundancy of the optimal solution. And this can be different things. I'm having two examples. The first example will be the so-called turnpike property of optimal trajectories. It's a property of optimal trajectories, so of these individual solutions of the system if you plot them in the d-dimensional space. And that's what I would call a temporal redundancy property. And the second is a property of the optimal value function, so-called separability of the optimal value function. That's a spatial redundancy property. Well, we will see how this can be used. Just to mention beforehand, so the turnpike property will turn out to be very, very useful for analyzing model predictive control, and I will also show you this use case there. And the separability of the optimal value function will turn out to be quite useful when analyzing deep reinforcement learning schemes. So both will be there as both techniques that. Okay, let me start with the turnpike property. That's, as I said, the temporal redundancy property. And to introduce that, I will look at a slightly different optimal control problem. And I will do this presentation entirely in discrete time, even though you can, of course, also do it in continuous time. So let's look at this functional here, which is the same as before, except that I have now truncated it, right? So it's n-1 instead of infinity up here. It's just a finite number of steps. What the informal description of the turnpike property is that any optimal trajectory stays near an equilibrium, which I always call xe here, e for equilibrium, most of the time. And yeah, let me show you a very simple example where this property occurs. Very simple means really one-dimensional, discrete time, linear, quadratic cost. It can't be simpler. So what do we have? We have a dynamics which just says each time when time progresses by one time step, the state doubles, right? So we go from x to 2x, and then the control is added. You immediately see that at least in the regime where we are, the system is completely controllable by adding the right u. I can jump from every point to every other point I wish. I just have to compensate for this 2x, right? We have constraints. The system is not allowed to leave this x and this interval minus 2, 2. And this is what makes it interesting, because if we didn't have constraints, we could just switch the control off, let the system run, because the state doesn't even appear in the cost. But since we have constraints, we have to counteract at a certain point to keep the system in this set x. And this will create some costs. And then the question is, how do we keep the system inside this interval minus 2, 2 with a minimal summed quadratic cost? That's the question. Okay, so obviously, the closer the state is to the origin, the cheaper it is to keep the system inside x, because the counteracting to the 2x is cheapest if we are exactly in 0. So the optimal trajectory should probably stay near xe, at least most of the time. And here you see what's happening if you do the numerical simulation. So this up here is the upper bound of the interval. Sorry, this here. This is the optimal steady state where it's cheapest to stay. This is the initial condition. This is the optimal solution for 5 steps. It goes a little bit into the direction of 0, but it doesn't really get there. It turns away. It takes a curve and goes up. The reason is that actually, in the terms of minimizing control effort, it's cheaper to go to the boundary of the admissible interval rather than really going all the way down to 0. But now what we do is I will increase the horizon here in steps by 2. So if we have 7, 9, you see what's happening. We always end up at the same point at the upper end of the interval. But in between, the time we spend near 0 becomes longer and longer. We also get closer and closer to 0. And that's precisely this so-called turnpike property. The question is, how do we formalize that? There are many different ways. There is exponential turnpike, there is integral turnpike. What I will present here is what could be called measure turnpike. While measure is very simple here, we have a discrete space, a discrete time space, so measure is just a point measure, it's just counting. Right? So what we do is we take some neighborhood of the origin, and then we just count the number of points which are not in this blue neighborhood. And if you do that for all these trajectories, then you see it's never more than 8. Right? There are never more than 8 points outside the blue neighborhood, no matter how long I make the horizon. And that's precisely one of the possible definitions of the turnpike property. The number of points outside the blue neighborhood is bounded by a number. That's important, independent of n. Right? And here it's 8. Bit more formal. In continuous time, you would then actually use the Lebesgue measure rather than the counting measure here, but otherwise nothing much changes. Okay, yeah, where does it come from? It was described quite early in works by Ramsey and von Neumann on economic optimal control problems. I think they didn't call it optimal control problem at that time, but effectively there were optimal control problems. The name turnpike property came a little later by Dorfman, Samuelson, and Solow. I think 2 of them got the Nobel Prize in economics later. Does anyone know what the turnpike is literally? Martin. Yeah. So literally, it's a pike, so a long piece of a long rod or so that you can turn, open and close, so a moving barrier. And the name turnpike then became the name of highways, like here at the Massachusetts Turnpike, because originally there were these barriers in front, right? So toll roads, particularly in the northeastern part of the USA. And these toll roads were what these 3 researchers they had in mind when they used the name turnpike property, because they said that turnpike property, this is another system which has this property, is like driving on a highway. If you start here, you first go to the highway, stay there as long as beneficial, and then you take an exit and go to where you want to go. That's what they describe, and that's how they got this name. Yeah, it was really popular in mathematical economy. I think most of the works until the 1980s were more or less mathematical economy, but then since about 10 years, there has been an explosion of papers on the subject, and several people in this room here were participating in that. So this is really something that's happening, and the applications are really manifold. So originally, and this is classical control from Brian Anderson and Peter Kokotovich, they looked at the synthesis of optimal trajectories, because if you know that you have the turnpike property, all you need to know, where is my equilibrium? How do I get there in a cheap way? How do I get away in a cheap way, right? So computing a long optimal trajectory is much easier if you only have to compute the 3 pieces. Learning in neural ODEs is a very fascinating application. A very, very recent one is that we applied this to optimization-based estimation, which I also like very much. And of course, model predictive control. That's the reason I became interested in all this stuff in the first place. And I will explain this in a few minutes after one more intermediate slide. And on this intermediate slide, I would like to quickly tell what this has to do with dissipativity. Yeah, what is dissipativity? Dissipativity is like an energy balance property of control systems. It exists for many systems, for many physical systems. This is the version for discrete time control systems. And it says that we have some kind of so-called storage function that you can imagine as some abstract function measuring some abstract energy. And we have this inequality here that the energy at the next time step is bounded by the energy we had before, plus something which is provided by the cost function here that we have of our problem, where this which is kind of shifted so that it becomes 0 in the equilibrium, and minus some additional term. This alpha is a positive function. It looks like that. It's 0 and 0, and then increasing, so that we always are dissipating a little bit of this abstract energy whenever we are not in the equilibrium. Right? And there are many, many nice consequences. I'm just mentioning the consequences that it has here in the context of optimal control. So it implies the turnpike property. So if we have this inequality, then we can use the turnpike property. It's actually equivalent to a robust version. Robust meaning turnpike property not only for the optimal trajectory, but also for near optimal trajectories, which have a slightly larger value. So then we really can go back from one to the other. which is a bit analogous, if you know that concept, for asymptotic stability, existence of a Lyapunov function, where this lambda would then play the role of the Lyapunov function. And in fact, these inequalities, they really give us some analytic tool to work with, which we can then use to build, for example, Lyapunov functions for the control systems. Okay, and that will be very, very convenient for model predictive control. So let me tell you what that is and why is this turnpike property and the related dissipativity property. Yeah, turnpike properties, as I said, they are really, really crucial for analyzing model predictive control. What's model predictive control? Let's go back to the problem we originally wanted to solve. This is this infinite horizon problem here. And then we compare this with the problem that we do solve. This is this finite horizon problem. This is much, much easier to solve. So this is essentially a nonlinear program for which many, many good solvers are available. Okay, so how can we approximately solve the problem up here using the problem down here? Well, the problem is, the idea is that we repeatedly solve the problem down, the lower problem, to get a feedback law. So here's a little sketch how this is done. So we start with a certain initial condition, then we solve the finite horizon problem here with, I think, 4 steps, right? And then what we do is we use the first control value, which means that we follow the first piece of that trajectory. And then we are at a new point, and then we optimize again with the same horizon, but now shifted ones, right? So we get a new so-called open loop optimal trajectory, open loop optimization. We follow that, we optimize again, we follow that. And this way we can generate arbitrarily long solutions from the first pieces of the finite horizon solutions. That's this moving horizon idea, which is all about model predictive control. Okay, so it's really, the feedback is not a formula. We won't be able to get a formula in general, but what we get is an algorithm which we can quickly evaluate, quickly enough to let this run. This pendulum was done with a predictive controller where we had 50 milliseconds for each optimization, which was feasible with I think it was an IP-opt implementation. So something off the shelf, nothing really fancy. Okay, so what happens if we apply this predictive control technique to a problem that has this turnpike property? It's the same as before with, I think, length 10, right? The initial value is a bit higher up than before, and what you see is if we follow that, we produce trajectories that start lower and lower. They thus get closer and closer to the turnpike, and what you see is that this movement away from the turnpike equilibrium, the so-called leaving arc, is never done by the predictive controller because the first piece never turns away. The trajectory first stays a little bit, and what we get is a trajectory that converges almost to this blue equilibrium, and that's precisely what an infinite horizon optimal trajectory should qualitatively do. It should converge to the optimal equilibrium. So the turnpike property really makes this work, and what we can do is we can prove the following convergence theorem that's already a couple of years old, together with a student of mine, Marlene Stieler. We did that. So let's assume that we have an optimal control problem that has this dissipativity property. And we assume, moreover, what we need is some regularity on the optimal value function, some equicontinuity property, but we only need it at this equilibrium. Far away, we don't care. Then we get 3 properties. The first is what is called semi-global practical asymptotic stability of this optimal equilibrium. Then we get some approximate transient optimality, and we also get an approximate averaged optimality. Since I assume that none of us, or very little of you, know what this means, let me illustrate at least 2 of them graphically, just to explain what that means. So let's look at the first 2 properties. So what does it mean that the closed loop is semi-globally practically asymptotically stable? Well, it means the following. Here we have the equilibrium, and what this means is that depending on the size of the horizon n that we use, so this is the length of the prediction we use in each step, we can find a function epsilon1, which tends to 0 if n tends to infinity, such that the optimal solution converges to this epsilon1 ball, and if it's in there, it stays there. What it does there, we don't know, but it gets close to the equilibrium. This is practical in practical asymptotic stability. Outside, it also has an asymptotic stability property, which I have not written here. That's the first property. It behaves almost up to a small error, which depends on the optimization horizon, like an optimal control, optimal trajectory, qualitatively. And now, what is this transient optimality? Well, let's fix some time k, and let us now look at all other trajectories, or say many other trajectories that start in the same initial condition, and move to this neighborhood here, right, where this red trajectory goes. Then what we can prove is that the trajectory that is generated by predictive control is actually the cheapest among all of them, again, up to an error which depends on capital N, right? So if we make n larger, the error will become small. If we make n smaller, so this means that the cost of all other trajectories reaching the ball at time k is higher than that of the MPC trajectory, right, up to a certain error term, which I will yet not discuss in terms of time. Okay, yeah, predictive control is something that was developed by engineers since the 1970s, so still today it's used very much in the engineering domain, and I would like to show you one use case, particularly one where this thing with the turnpike is not so trivial and where you can probably get some insight about how you can do that. That's the optimal startup of what is called a combined cycle power plant. These are huge things. These are power plants that produce electrical energy from gas by using a combination of gas and steam turbines. So the key idea is that the exhaust gas, the hot gas that comes from the gas turbine, heats up water, produces steam, and this steam then goes into a steam turbine. So the heat is used twice, and this makes this very, very efficient. They can actually, this is like the schematic sketch of such a thing. So here we have the generator, here we have the gas turbine, the exhaust goes into the steam generator, and the steam then goes into the steam turbine, which is over here. Yeah, and they can reach up to 64% efficiency just for generating the electrical energy. If you use the remaining heating for some, say, district heating, for example, then you could get even better. The important thing is now, well, these gas power plants, of course, they are preferable to, say, coal and other power plants, not only because gas is a little bit better in terms of CO2. Maybe if we use green hydrogen in the future, they are much better than that, but also because they are much more flexible. You can really power them up quicker, but quicker doesn't mean quick. It still takes conventionally much more than an hour from a warm start, right, from a preheated power plant until they can really produce electrical energy. And the goal of this project was to develop strategies that allows for a flexible, fast, and also economic startup, better than what could be done before. So the objective was to reach a certain desired load level so that we can then connect the generator to the grid with minimal fuel consumption. That was the idea. And the constraints, of course, we have to avoid all kinds of catastrophes, too high pressures, explosions, and so on. That's for sure. A bit more subtle is that there's also, I mean, this is a huge system, right? So they have a lot of underlying low-level control, which controls all kinds of subsystems in this huge power plant. And we should not compute any control strategy with a predictive controller that contradicts them, right? So we have to kind of take into account that there are constraints from the underlying low-level system. And this is the most important thing that distinguishes this predictive strategy from the conventional strategies. We want to be optimal in the sense that we would like to avoid excessive wear and tear, and this is mostly the thermal stress that arises when the steam temperatures are rising much faster than the wall temperatures of the big pipes, right? So we should avoid large temperature gradients in the pipes while powering up the power plant. That's the idea. Okay. So the model is a classical first principle model, depending which models are the components. Let me go over this very quickly. It's really just mass conservation, energy conservation, heat transfer. Here's a heat equation hidden in there, so this makes it a partial differential equation that we get in the end. Kinetic energy, work performed by turbines, and so on. there's a lot of model reduction, of course, going on, and in the end, they identified a model which has just 30 what is called differential states that really appear in differential equations, but still a lot of additional states which are algebraic states. They depend in an algebraic way on these differential states, and a lot of constraints. So the model is not huge, but it's still reasonably big, and actually quite big for online optimization still. What is the optimization objective? Yeah, we just define a function which is 1 if the desired load level is not yet reached, and 0 if it's reached, and phi of t is the fuel consumption at a certain time, and then we just integrate over that over an infinite horizon. Okay. Yeah, what about the turnpike here? Well, obviously the turnpike is somewhere in the region where the power plant has reached the load level, right? This is where the optimal equilibrium should sit. We don't know where exactly it is there. This depends on the precise dynamics, but it must be somewhere up there. And somehow the optimizer, of course, has to see this, right? So we have to choose the prediction horizon, this n, capital N time step, so long that we can see where we have to go. And now, of course, you could design your cost function in a way that it guides you to that point, meaning that we can use a rather short horizon. But actually, what's happening here is that we have this cost which is just 0, 1, and also at Siemens they didn't want to change that. So this is not what's happening here. So we really need to have a rather long horizon. So what happens is, in fact, we need a simulation time of about 1 hour, and it turns out that this is completely prohibitive for online implementation. So the optimization is, first of all, over that long horizon quite unstable, so you very often have to reinitialize, try again, and then it takes way too long, right? You can't implement it that way. So what's the trick? Well, the trick is to compute this optimal startup trajectory beforehand and then just track certain quantities, right? So what we solve in the online phase is actually just we minimize the distance of certain important quantities to the quantities of the optimal startup trajectory. And that's not only in this case technically motivated, but also the usual way these power plants work these days is that they have to say 1 day ahead when they start. So this is also, in fact, so very consistent with the practice that power generation is scheduled 1 day ahead on the German electricity market. So they have to compute the startup on the day before anyway, and then they can also use it for this tracking purpose. Yeah, what happens then is, of course, for the online problem, the turnpike is now not an equilibrium, but some time-varying path near the reference trajectory. So you can extend this turnpike theory to time-varying problems. That's what you have to do here. And then, of course, a prediction horizon of few minutes simulation time is suitable, and this is perfectly real-time implementable. Of course, there's one thing. We wouldn't like to start too far away from this reference trajectory, but the initial state of the plant is, of course, not precisely known the day before when you compute that. So what is in practice done is they compute a kind of library of different startup trajectories, and then at the online time they choose the best one that fits best to the current state and use that. Okay, here are a few pictures. What you always see is dashed lines. Dashed lines are this is from a real plant, right? A real power plant somewhere in Germany. I'm not allowed to tell you where it is. These dashed lines are the conventional startup they used before. The black line is this reference trajectory they have been using. They have computed the day before. And the solid lines are what the plant really does when they try to follow the trajectories. They don't want to follow that exactly, they just want to track a particular quantity. What we see here is the plant load, and 1 here is the level we want to reach, and we see that we save about 40% of time with the optimized strategy. We also save about 40% of fuel. This is the fuel consumption. It's almost the same, right? You see that it's neither more nor less fuel, so the fuel amount that is used is the same. So the decisive trick is not that they somehow do something quicker or faster here. The decisive trick is this, what is called this HP bypass valve. That is HP is the steam turbine. And the bypass valve says how much steam is not going to the turbine. So the lower the value, the more steam goes to the turbine. And what the predictive controller does is it sends the stream to the turbine much earlier in the startup phase. So it does a quicker, but also more gentle warming up. And more gentle actually is also shown not here, but here. You see this heat stress, this wall temperature difference, and you see that the predictive controller is not only faster, but it's also much more gentle to the pipes, right? It avoids this very high temperature differences that the other thing does. So it's really better in several respects, and I think a very nice application to a highly non-trivial problem of this predictive controller. And yeah, some knowledge about how this turnpike theory works was really helpful in designing. Okay, I've already used way too much time, so maybe a few more minutes that I have for the separability issue. Okay, reset. We are not computing trajectories. We are now trying to compute the optimal value function and getting the feedback from that. So recall, this was the optimal value function, and what is done in so-called deep reinforcement learning is that a deep neural network is used to store this optimal value function. Okay, sometimes they do not store the V, they store something they call Q, but you can consider this as almost the same. It's a little bit different, but it has the same purpose. Okay, what's a deep neural network? Here we have a not so deep neural network with 2 layers. What's happening is, yeah, we send in here the input value, which is our state vector, x1 up to xd. So each element here is a scalar value. What's happening is this is processed. We take a scalar product here, we add some so-called bias term, and we send it to a nonlinear function. And by this, we produce the values in this first level of neurons here, these blue circles. And then we do exactly the same on the next level, except that here we base the computation on the values here. We compute the values here, and then some affine linear combination of the values here makes the output. And this output should be, well, as close as possible to the optimal value function for the input vector I put in here. Yeah, there are a lot of parameters here. All these W's and B's and A's and C's are the parameters. We just put them together into this vector theta here. This is the vector of all parameters. And these activation functions in each neuron are scalar functions. They can be as simple as the identity. They can be this so-called ReLU function. So this is the maximum between R and 0. This is like a smooth approximation. This is a classical sigmoid function that is used very often. So there are different choices. Bottom line is this network represents a function from Rd to R. And what kind of function it is depends on the parameters in theta, right? So we have to find good parameters so that eventually we get this approximation here when we find the right parameter vector theta star. Okay, yeah, and in deep reinforcement learning, what is done is we try to train our network so that either the Hamilton-Jacobi-Bellman equation or the Bellman equation are satisfied as good as possible. So that's the criterion, right? The training itself is an interesting, highly non-trivial and also often very difficult problem. I will not talk about that. I would like to talk about a more fundamental question, namely, assume that we have a high-dimensional system. Is it possible to represent such approximations? So it's not, so whether we can compute them is another difficult question, but the first question is, is the network able to represent this function, right? If we have a high-dimensional space, right? And yeah, the first thing you have to look at, and Enrique mentioned Cybenko, is the universal approximation theorem. This tells us what kind of functions these networks can represent. And the statement is, and I'm going over these function spaces quickly, that's nothing too complicated. The bottom line is that actually, even for very simple neural networks with one hidden layer, given any epsilon, we can find a network that is able to approximate any function from this class with an approximation accuracy at least epsilon. And okay, that's good. The not so good thing is the number of neurons usually behaves like the order of epsilon to the minus d. And if you think a little bit about that, you said, wait a minute, that's again exponential, right? So it's again an exponential growth in D. So this theorem tells us, great, these networks are really good. They can represent every function from this class as accurate as we wish. But the price we pay in terms of number of neurons, which we all have to compute, all the weights which are in there, and all the bias terms, is again exponential in the dimension. So to get something better, we have to restrict to suitable classes of functions, and this is now where the separable functions enter the stage. And separable functions are something very simple. It's just a high-dimensional function which can be written as a sum of lower-dimensional functions. So each of these wj vectors is a subvector of the original state vector x with at most or with exactly dj components. So if this is a vector in Rd, this is a vector in Rdj, and dj should of course be smaller than that. What we can then do is we can then approximate these individual functions by subnetworks, by smaller subnetworks, and the number of the subnetworks, if the dj does not grow, it grows only linearly with a dimension, right? And that's the trick. So we can, by using this structure, we can break this exponential growth and turn it into a linear growth of subsystems. When you then do the calculation, you'll see that the number of neurons grows a bit faster than linearly. So what we essentially do is we apply the universal approximation theorem separately in each gray block. And then we can see that the separable functions, they can actually be approximated with a number of neurons that grow only polynomially in D. Of course, the important thing is that we have a D max, which is independent of the overall dimension, that limits the dimension of these subsystems here, right? And we can actually even compute them, and the D max then appears here in the exponent, so it's polynomial, but not exponential anymore. Okay. The question is now, is there any chance that an optimal value function has this separable structure? And the answer is, in general, no. Optimal value functions will not be separable, but maybe we can approximate them by separable functions. Maybe this is possible. So let me quickly go into that. So the idea here comes from what is called distributed optimal control. There we assume that our system can be decomposed into S subsystems. They all have their own state Zi, and the states of the other subsystems enters here as an additional argument, right? So that minus I is everything except Zi. And the interconnection is expressed via a graph, and this graph has an edge between two nodes whenever Fi depends on Zj, right? So in this case, for example, either F1 depends on Z6 or F6 depends on Z1. It's undirected, so we can't tell which, but then we have this connection. Then we can talk about distance of subsystems. The distance of subsystems is just the number of edges I need to cross to get from one to the other. So for example, the distance in the graph between subsystem 1 and 11 is 1, 2, 3, 4, right? I have to do 4 hops to get from Z1 to Z11. This is precisely the 4. Okay. Then, of course, we have the cost in our optimal control problem. We assume that the cost can also be written in the separable form. And then, again, we have to consider those links in the graph if we have some Zj appearing here in Li, right? So the graph structure is determined by the Fi and by the Li. Whenever one of the two is connected, we have this edge. Okay. And the question is then, how does the state of a subsystem influence the optimal trajectory of a subsystem far away? And before I give you a theoretical result, I would like to show you a little simulation again. This is an example where we have a convoy of trucks, and they should drive on the road and keep a fixed distance from each other. So what is known is that if you design the controller not very carefully, you can actually create instabilities. If the first car has to brake, the second has to brake a bit faster, the third even more, and then you get this accordion effect in the line. Very nice student exercise that you can do in a seminar. However, if you do it optimally, then this should not happen, right? And here is a little optimal control problem. Each vehicle is just a double integrator with position, velocity, and acceleration. we compute a control that minimizes the following functional. So we have some reference for the first vehicle where this should be. This here penalizes the deviation of the distance capital L between two consecutive cars. Then we have some regularization terms which ensure that the matrices that we get, if we write this down, are positive definite so that we can apply what is called Riccati theory. That's an established solution theory for these kind of problems. Yeah, we have solved that for 100 vehicles. I'm showing you the first 5. The dashed line shows where the vehicle should be. And here you have an initial condition where this vehicle had to do a braking maneuver before. So it's not at its position, it's actually very close to the position of the second. This is the time when we start the regulation. The second, of course, has to brake, but since it knows that the first one is already on its way back to its position, it doesn't brake very much, right? And the third one brakes even less, the fourth even less, and in the fifth you can hardly see this. So what we have is we have some kind of decaying sensitivity. The perturbation that happens in one vehicle gets faded out or damped out while it propagates through this whole convoy of trucks. Okay, now here is a theoretical result that confirms that this will happen in a general class of results. So we have linear quadratic optimal control problems. We have then in these kind of problems, we know that the optimal value function has this particular form. So it's x transpose px. And the optimal feedback is actually a linear feedback. So it's just a matrix times a vector. Then what these colleagues from, I think Shin is at MIT now, have proven is that under suitable uniform stabilizability detectability assumptions, we have this inequality here, namely that the norm of this Kij block, that's the block that maps the state of the J system to the control of the I system, is bounded by a rho, which is between 0 and 1, to the power of the distance in the graph. So the larger the distance is, the higher becomes the power, and the smaller this parameter becomes. So the sensitivity, so the influence of a system on the other, decays exponentially with the graph distance. That's what it says. Okay, yeah, we have then shown, and it was just a corollary, that we can get the same for the Pij matrix, for this one, for the blocks. And this can now be used for the creating the exponential separable approximation. So what we do is we want to approximate V by a separable function, and let me quickly go there. How do we do that? We do that, let's assume that we have a very simple graph. So the graph distance is just I minus j. This is like in the convoy, right, where we have this linear structure one behind the other. And then what we can show is that, or what you can see is that under this decay of this Pij, if you look at the difference of two value functions, and you look at the same difference, but here we set all the, after a certain index, after the index k plus l plus 1, we set everything to 0. This is almost the same. And this allows us to define this as this constituent function of our separable approximation. We get this approximation, and we can actually show that the error depends on precisely this rho that sits in this estimate for these matrices here. So the rho determines how good this is. This works on arbitrary L2 balls. The size of the ball determines how large this constant. Okay, if the graph is a bit more complicated, we have to take into account how fast it grows if you go like through the graph. And it's not allowed to grow faster than this thing here decays, so we have to grow slower than rho to the minus L. If that's done, if that's true, then we can generalize this. Yeah, we have a nonlinear version. In this case, we don't have a quadratic function anymore. We then, instead of looking at the blocks of this matrix P, which does not really exist anymore, we look at the Lipschitz constant of this map. And if the Lipschitz constant satisfies a certain, this has also this exponential decaying, then we can also build this kind of approximation. We can also get something for slower than exponentially decaying sensitivity. So we have just a polynomial term here, not an exponential. We can still do something. And the important question is, of course, now when do the Lipschitz constant Lij of this map here satisfy this inequality? So what we need is a nonlinear, non-quadratic version of the theorem I showed you before by Shin et al. And we are on the way. We have some good ideas, but it's not yet ready to be written. But I'm confident that in a couple of months we will have some. Okay, let me stop with a quick numerical test. We look at a very simple linear quadratic problem with, where A is a randomly generated banded matrix, 200 times 200, and then you see very nicely that you get this decaying sensitivity. Just plotted the norm of this P, so it really goes down exponentially fast down to machine accuracy. At that point, a couple of weeks ago, someone in the talk asked, well, the usual way we would consider simple matrices would be by looking at their singular values. Does this P also have a nice structure with their singular values? The answer is no. Singular values decay very slowly, so a low-rank approximation is not what you could do in this stage. It doesn't mean that there might be other approximation techniques, but this is really something which is at least different from the classical low-rank approximation. That's the network we used for the numerical test. It has this separable structure. It does not have this layer which distributes, because here we already know which axis we want to send into which of these gray blocks. We did not really do reinforcement learning in order to avoid all kind of noise from improper learning. We did supervised learning because we know V with other techniques, so we can compute that. And then what we see is that for the 200-dimensional problem, we get down to a mean square error of about 10 to the minus 3. So much about the high accuracy we discussed this morning. So this is not high accuracy, but it's okay, right? It's not so bad. Right? That's what we could do in 200 dimensions. You see on the left what the neural network says, on the right the true value function. Of course, this is just a two-dimensional projection of that. This is interesting. We have then increased the dimension from 20 to 120, and always by reducing the number of neurons, try to find out with how little neurons we can still maintain this accuracy of 10 to the minus 3. And it turns out that the number of neurons grows linearly, so not exponentially, but also not polynomially. It's really a linear growth. So this really seems to work. We have no exponential growth. Why it's not polynomial, we don't really know. There may be different reasons afterwards. And the last thing we looked at is the question, well, of course you can do that, but does it pay off to use this particular separable structure? Can't we simply take a fully connected network, right? This can represent all the functions the other does and even more. So what's the benefit of using the separable structure? And the answer is, well, the training is much easier, right? The number of samples that we need is much smaller to get to a certain accuracy. And also the number of, this is the number of samples. The other was the number of, let's go back. This is the number of epochs that we need for training. Training data point. This is the number of training, this is the error. So this is the number of data points. So with a much smaller number of data points, we get to a much higher accuracy with the separable network. And this is the number of epochs here that we need to. The number of epochs for training gets much larger in the fully connected network. The fact that here we have to learn much more weights and parameters really slows down the training. So if you know something about the structure and if you use it, you can be much more efficient. Okay, yeah, we have some ideas how we could prove that, going back to approximation theoretic literature, but let me skip that and come to the conclusion. I've been talking way too long anyway. Okay, so in general, if you want to solve infinite horizon optimal control problems, the numerical effort grows exponentially with a state dimension. And you need a certain redundancy to make this problem solvable in high-dimensional spaces. And the turnpike property is a property that makes optimal trajectories simple. So we can compute them by putting together pieces of trajectories which are simple to compute and can actually construct the feedback law on the fly, like online with online computations. And the separable approximation they provide us with a method where we can at least show that at least the representation of optimal value functions for high-dimensional problems can be done with deep neural networks. Actually, not so deep, but at least a little bit deep. Okay, yeah, and like decaying sensitivity is a very interesting property that I came across in this, and I really like that very much. Yeah, with that, I'm done, and thank you very much for your attention.